So let's discuss about an interesting locus problem which says that find the locus of a fixed point on a circle of radius a rolling inside another circle of radius 4a. So we are talking about something like suppose this is a circle with center at the origin having radius 4a and another smaller circle having radius a that is like starting from here and is continuously rolling inside the bigger circle. Okay, then we need to find the locus of a fixed point on the circle. So suppose the fixed point is p dash and the center of the smaller circle is c dash. So we are talking about the locus of this point p dash as this circle will continuously roll on the inside the bigger circle. So you see that the point p dash will be traveling to newer positions as the circle will be rolling on the bigger circle inside the bigger circle. Now the point is that I have taken two particular position of the circle, like this is one position and this is another position. Now we can safely assume that this arc length that is traveled by the circle must be equivalent to the arc length traveled by the point P, which is the new position of the point P dash. This is the starting position of the fixed point and this is suppose the transformed position of the point P dash, that is P. So we can safely assume that the arc length that is traveled by the smaller circle should be equivalent to this particular arc length that is traveled by the point P, because initially the point P was here. So first of all we can write down that the arc length traveled by the circle, that is this particular arc length, and this particular arc length will be 4a, that is a radius, into theta. So first of all we can definitely write down that 4a into theta must be equal to the arc length that is rp, this particular arc length traveled by the point P, and that particular arc length will be a into the angle rcp. So from here we can safely say that the angle rcp should be equal to 4 theta, and this angle should also be theta because this is horizontal, that is parallel to x-axis, and so we can say that angle PCQ should be equal to 4 theta minus 90 degree, because this is an horizontal line and this is a vertical line. Now the construction is that from the center C we have drawn a vertical line on the x-axis, and P is the new position of P dash. So from P we have dropped a perpendicular PM and a perpendicular PQ on CN. So we can say that the angle PCQ must be equal to the total angle is 4 theta minus 90. So angle PCQ will come out to be 3 theta minus 90. Now we need to find the locus of the point P, locus of the moving point P. So to find the locus of the point P, we need the x coordinate and the y coordinate of the point P. So we can see that the x coordinate of the point P is nothing but OM, and that x coordinate OM can safely be written as ON minus MN, and which is equivalent to ON minus MN is nothing but PQ. Now from the figure we can see that ON, the length ON is the horizontal component of OC. Now the length OC can be safely said to be 4a, that is the radius of the bigger circle, that is OR, minus the radius of the smaller circle. This much is the radius of the smaller circle A. So OC is nothing but equivalent to 3a. So ON can be said to be the horizontal component of 3a. So 3a cos theta minus the length PQ. The length PQ can be said to be PC sine of the angle PCQ, and the angle PCQ is 3 theta minus 90, so it will come out to be 3a cos theta minus the length PC is nothing but the radius of the smaller circle A sine 3 theta minus 90, and which on calculation will give us 3a cos theta plus a cos 3 theta. Now if we apply the formula of cos 3 theta, then it is known to be 4 cos cube theta minus 3 cos theta. So we can see that 3a cos theta term is actually getting cancelled, and we are having the distance OM to be equivalent to 4a cos cube theta. Now this is the x coordinate of the point P. Now let us come to the y coordinate of the point P. To find the y coordinate of the point P, we are interested about PM, that is the perpendicular on the x-axis. So PM can be written as the distance Qn, and the distance Qn can safely be written as the distance Cn minus Cq. And the distance Cn can be written as 3a sine theta, okay, because this is 3a and this is theta, so this Cn should be the vertical component of 3a sine theta. So 3a sine theta minus the distance Cq can be written as Cp cosine angle PCQ. Okay, this is Cp, which is the hypotenuse, so Cp cosine angle PCQ will be Cq. So in this case it will come out to be 3a sine theta minus a cos theta minus 90, 3 theta minus 90. So this time it will come out to be 3a sine theta minus a sine 3 theta. And if we apply the formula of sine 3 theta, then we can easily say that this is coming out to be 4a sine cube theta. So this is the y coordinate of the variable point P. So to find the locus of the point P, we can safely assume that the x coordinate of the point P is 4a cos cube theta, and y coordinate of the point P is 4a sine cube theta. So from these two we can safely say that the value of cos square theta will become equal to x upon 4a to the power 2 by 3, and from here the value of sine square theta will come out to be y upon 4a to the power 2 by 3. So we can eliminate the parameter theta to get the locus, and so for eliminating we know cos square theta plus sine square theta will come out to be 1. So that implies the locus equation will become x to the power 2 by 3 plus y to the power 2 by 3 is equal to 4a to the power 2 by 3. So this is going to be our locus equation. And just to give you the idea, this is the equation of an asteroid. This is the famous equation of the asteroid locus, which can be verified to be having a figure like this. So this is the locus equation of, this is the locus diagram of an asteroid having an equation x to the power 2 by 3 plus y to the power 2 by 3 equal to some constant to the power 2 by 3.